Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So, in the previous modules we have looked at the operation of the schematic, the operations at the transmitter, the operations at the receiver in an OFDM wireless communication system, the system model for an OFDM wireless system. So, today let us look at the bit error rate performance of an OFDM system, alright. So, to characterize the performance of an OFDM system similar to what we have done before, let us look at the bit error rate of an OFDM system. I hope everyone remembers this by now. BER stands for the bit error. This stands for the bit error. This stands for the bit error rate, and OFDM is orthogonal frequency division multiplexing. Okay, so we are looking at the bit error rate of an OFDM system, and we have seen that the OFDM system, the system model can be expressed as the received signal Y equals the channel H circularly convolved, the channel H circularly convolved with the input X, and previously we have ignored the effect of noise. Let us now add the noise. So, W is Gaussian noise. So, now we are adding Gaussian noise. We are adding Gaussian noise to this, and now once we take the FFT at the receiver, after, remember, in OFDM we take the FFT at the receiver, we have Yk equals Hk times Xk, where Xk is the symbol on the kth subcarrier, plus, since the FFT operation is a linear operation, plus Wk, where Wk is the FFT of the noise. So, we have Yk is the kth FFT point of the received signal Y0, Y1, Yn minus 1, this is the kth FFT point. Wk, capital Wk, this is the kth FFT point of the noise samples small w0, small w1, small w of n minus 1. So, what we are saying is very straightforward. We are saying that in time domain we have the received signal small y is the channel H circularly convolved with the input signal or the transmit signal X plus the noise small w at the receiver. Now, after taking the FFT at the receiver, we have capital Yk, where Yk is the kth FFT point of the received samples Y0, small y1 up to small yn minus 1 equals capital Hk, where Hk is the kth channel coefficient, that is FFT of the 0 padded channel coefficients H0, H1 up to HL minus 1 followed by n minus L0 times capital Xk, where capital Xk is the symbol transmitted on the kth subcarrier, plus capital Wk, where capital Wk is the noise, is the kth FFT point of the noise sample small w0, small w1, small wn minus 1. In other words, the noise Wk is given as, I have Wk equals, Wk equals k equal to, or I have L equal to 0 to n minus 1 small w of L e to the power of minus j to e to the power of, that is e to the power of minus j, e to the power of minus j 2 pi k L divided by e to the power of minus j 2 pi k L divided by n. Okay, so capital WK is the kth FFT point. This is the kth FFT point of the noise samples. This is the kth FFT point of the noise. And what we are going to assume about the noise samples is each WL is IID Gaussian, is independent identical Gaussian. So, the WLs are IID Gaussian and also 0 mean, which means expected value of WL, each noise sample WL is 0, expected value of magnitude WL square equals sigma square, that is the variance is sigma square, and expected value of WL times WL tilde conjugate, that is the correlation between noise samples L and L tilde is 0 because these noise samples are independent. So, what we are going to assume about the noise samples are WL or the small WLs rather, the small WLs are Gaussian, these are Gaussian, these are 0 mean, that means to say expected value of WL equals 0, expected the noise power is sigma square, which means expected value of magnitude WL square is equal to sigma square. Further, the noise is IID independent, which means expected value of WL into WL tilde conjugate, that is two noise samples L and L tilde are independent, are uncorrelated. Therefore, the correlation expected value of WL times W conjugate of L tilde is equal to 0. So, the noise samples are Gaussian, they are IID independent identically distributed, and also the noise samples are the noise samples. So, the noise samples W0, small w0, small w1, small wn minus 1 are IID, that is independent identically distributed Gaussian, and they are 0 mean. Okay. Now, let us look at the properties of WK. Now, let us look at WK. If I look at WK, which is summation L equal to 0 or summation L equal to 0 to n minus 1 small w of L e to the power of minus j 2 pi k L divided by n, I have expected value of WK equals expected value of L equal to 0 to n minus 1 small w L e to the power of minus j 2 pi k L by n equals summation L equal to 0 to n minus 1 expected value of W L e to the power of minus j 2 pi k L divided by n. Now, since expected value of each W L is 0, this whole quantity is 0, which means expected value of W k I have, therefore, expected value of each capital W k is 0. That is, since the FFT is a linear combination, the noise samples, at the input of the noise samples, each noise sample is 0 mean, and since the FFT is a linear operation, so naturally at the output of the FFT, that is each capital WK, the mean of the each noise sample capital WK at the output of the FFT is also 0 mean. Alright, so no surprises there. So, each noise sample the capital WK on each subcarrier is also a 0 mean. Now, let us look at the variance of each noise sample. Let us look at expected value of magnitude W square, and let us ask this question, what is this? Expected value of magnitude W square equals expected value of WK times expected value of W conjugate of k, which is basically I can write this as expected value of Wk equals summation L equals 0 to n minus 1 WL e to the power of minus j 2 pi KL divided by n times summation L tilde equals 0 to n minus 1 W L tilde e to the power of minus j 2 pi K L divided by n conjugate, which is equal to, I can write this as expected value of summation L equal to 0 to n minus 1 summation L tilde equal to 0 to n minus 1 W L, simply I am taking the product of these W conjugate L tilde e to the power of minus j 2 pi k, of course here there is an L tilde, L minus L tilde divided by n. And now if you look at this inner expectation, if I take the expected value of WL, WL tilde conjugate, we already said that the noise samples WL and WL tilde are independent, therefore uncorrelated. Therefore, the expected value of WL times W conjugate of L tilde survives only when L is equal to L tilde. Therefore, I can simplify this as summation L equal to 0 to n minus 1 summation L tilde equal to 0 to n minus 1 expected value of WL W conjugate L tilde times e to the power of minus j 2 pi k L minus L tilde divided by n, and this is equal to 0 if L is not equal to L tilde equal to sigma square, that is if L is equal to L tilde, we have expected WL, W conjugate L, which is expected value of magnitude WL square, which is sigma square. So, this is equal to sigma square if L equal to L tilde. So, it only survives if L is equal to L tilde, at which point this is L equal to 0 to n minus 1 sigma square, and this is of course e to the power of minus j 2 pi k L minus L tilde. If L equal to L tilde, this becomes e to the power of 0, which is 1 sigma square times 1. Therefore, summation of sigma square from L equal to 0 to n minus 1, therefore, this is n sigma square, and hence I can write the variance of the noise at the output expected magnitude W capital W k whole square equals n times sigma square. So, what we have is at the output of the FFT, the noise capital W k is 0 mean and it has a variance of n sigma square. Further, since each W k capital W k is generated as a linear combination of the small w k's, that is, it is a linear combination of Gaussian input noise samples, therefore, each capital W k is also Gaussian. Therefore, as a result, the noise can be characterized as follows: the noise at the output of the FFT, each W k, this is Gaussian, expected value of W k equals 0, the variance of the noise, that is expected value of magnitude W k square, that is equal to n sigma square. So, we have characterized, and this is the noise variance at output of FFT. What is this? This is the noise variance at the output of the FFT operation at the receiver. So, we have characterized the noise, the properties of the noise at the output of FFT. Now, let us characterize the property of the channel coefficient capital H of k. Remember, capital H of k is given by the FFT of the 0 padded channel coefficients H0, H1 up to H capital L minus 1 followed by N minus L0. So, capital HK equal to kth FFT point of the 0 padded sequence H0, H1, HL minus 1, 0, and what is this? These are N minus L zeros. Hence, if I write the expression for H of k, naturally H of k is given as summation L equal to 0 to N, and since there are only L coefficients, capital L minus 1 H of L e to the power of minus j 2 pi k L divided by N, correct. Since there are only capital L minus 0 to capital L minus 1, the rest are zeros, therefore, the FFT point is simply given as summation small l equal to 0 to capital L minus 1 H of small l e to the power of minus j 2 pi k L divided by N, that is expression for the kth FFT point. What we are going to now assume that each HL is 0 mean, the expected value of each HL, that is each HL is a Rayleigh fading channel coefficient, which means each HL is a complex Gaussian, which means each HL is 0. Together we are going to assume that expected value of HL times, and this is an important assumption, expected value of H conjugate L tilde, this is equal to 0, that is the noise, that is the channel taps L and L tilde are uncorrelated. This is termed as the uncorrelated scattering assumption, this is termed as uncorrelated. This is termed as the uncorrelated scattering assumption. So, what are we assuming? We are assuming that each HL, each channel coefficient HL is a Rayleigh fading channel coefficient, which means each HL is complex Gaussian, right. We are assuming that each HL is 0 mean, expected value of HL is 0. Expected value of two different channel coefficients, that is the correlation between two different channel coefficients, expected value of HL times H conjugate L tilde equal to 0, which means the channel coefficients HL and HL tilde are 0, which means that the coefficients are uncorrelated. This is known as uncorrelated scattering, this is known as an uncorrelated scattering environment, and also we are going to assume that the power of each HL, that is the standard Rayleigh fading coefficient, expected value of magnitude HL square, is identity. So, what are we assuming? We are assuming the various HLs are Rayleigh fading which means each HL is complex Gaussian expected value of each HL is 0, expected value of each magnitude HL square is equal to 1, that is average power 1, and also we are assuming the uncorrelated scattering. Which means expected value of HL times H conjugate L tilde equal to 0 when L is not equal to L tilde. So, we are assuming the uncorrelated scattering example. And now again I am not going to go through the details again, but if I look at the expression for H of k, each H of k is summation k L equal to 0 to capital L minus 1 H of L e to the power of minus j 2 pi k L by N. Each HL is complex Gaussian which means it follows that the Hk, which is a linear combination of the small HLs, this is also complex Gaussian. The capital Hk is also complex Gaussian, which means Hk is also Rayleigh fading in nature. This means Hk is also Rayleigh fading nature. Each of the small HLs has 0 mean, which implies HL is also 0 mean, that is expected value of H of k is equal to 0. Further, each of the small HLs are uncorrelated, therefore it follows that expected value of magnitude Hk square is equal to summation L equal to 0 to L minus 1 expected value of magnitude small HL square, magnitude e power minus j 2 pi k L over n whole square is 1 anyway. So, this summation L equal to 0 to n L minus 1 expected value of magnitude HL square, which is summation L equal to 0 to L minus 1 of 1, which is therefore equal to capital L. So, what we have at the end is that each capital Hk is in turn a Rayleigh fading coefficient. Each capital Hk is a Rayleigh fading coefficient. This is a Rayleigh fading coefficient with 0 mean, that is expected value of H of k equal to 0, and average power, that is if I look at expected value of magnitude Hk square, this is equal to L, correct. So, each capital Hk, that is a kth FFT point of the 0 padded channel coefficients H0, H1 up to HL minus 1, these are 0 mean. Capital Hk is Rayleigh fading in nature, it is 0 mean, it has average power capital L, correct. So, now if I look at my system model across each subcarrier, I have Yk equals capital Hk xk plus nk. So, this is Rayleigh fading average power L, this is Gaussian noise expected, that is noise variance expected magnitude W square equals n sigma square. Let us assume a power of P, that is magnitude xk square equals P. Therefore, the SNR of this, for this problem my SNR equals magnitude Hk square P divided by n sigma square, that is SNR at the receiver. But magnitude Hk square is L, therefore, average of the received power at the receiver. So, what we are saying is the following thing, the SNR at the receiver, this is SNR at receiver, SNR at equals magnitude of Hk square P, where P is the symbol power, divided by n sigma square, but each magnitude of capital Hk square, the average power is capital L. So, there is an SNR scaling by capital L, since the average power of the magnitude Hk square is capital L, there is an SNR scaling by L. So, the way to talk about this is the average of the received SNR, the average of the received SNR is Lp divided by n sigma square. Therefore, since the channel is Rayleigh fading, the bit error rate for BPSK transmission is half times 1 minus SNR, average of received SNR divided by 2 plus received SNR. So, this is L over n times SNR divided by 2 plus L over n times SNR, where SNR is, using our standard notation, is P by sigma square. This is the transmit SNR, this is the transmit SNR, therefore bit error rate. Let me box this thing so that it can be, it's clear for all of you to refer to this thing. So, the bit error rate of this OFDM system is half into 1 minus square root of L over n SNR by 2 plus L over n SNR. This is the bit error rate of my OFDM system. This is the bit error rate of the OFDM system. Let us do a simple example to understand this bit error rate. So, what I am doing is I am trying to do a simple example to understand the bit error rate of this OFDM system. So, we want to calculate the bit error rate of OFDM system with L equal to 16 channel taps L equal to 16 channel taps, N equal to 256 sub carriers, N equal to 256 sub carriers, and my SNR equals 35 dB. The dB SNR is 35 dB, which is basically my P power sigma square. And my question is, for this system, what is the bit error rate? So, I have an OFDM system with L equal to 16 channel taps, N equal to 256 sub carriers, and an SNR P by sigma square, which is dB SNR is 35 dB. We are asking what is the bit error rate of this OFDM system, and as we know, we have dB SNR 10 log 10 SNR equals 35, which means SNR equals 10 power 3.5. The bit error rate of this system is half 1 minus square root of L over n SNR divided by 2 plus L over n SNR, and this is equal to, now we are given L equal to 16, N equal to 256. So, this is equal to half 1 minus L over n, that is 16 divided by 256 times SNR, which is 10 to the power of 3.5 divided by 2 plus 16 divided by 256 into 10 to the power of 3.5, which is equal to, the bit error rate is 2.5 into 10 to the power of minus 3. So, this is the bit error rate of the OFDM system. So, for this example, we have been able, using the relation that we have derived for the bit error rate, we have derived the fact that the bit error rate of this system is 2.5 into 10 to the power of minus 3. So, we have been able to show, we have considered an OFDM system, right, we have looked, we have added noise. So, now we have considered, in this module we have considered the noise at the receiver, which we have previously ignored. Then we looked at the effect of the noise. In particular, we have derived the properties, the statistical properties of the noise, that is the mean and the noise power. We also characterized the channel coefficient across each subcarrier, and hence we have been able to derive the bit error rate performance of this OFDM system across each subcarrier, and we have also seen a simple example to calculate the bit error rate performance of this OFDM system. With this, we will conclude this module. Thank you very much.